All right, so let's see the reminder. Tutorial for this week should be week number 3. Sorry, not 2. Okay, just to let you guys know, this week I cannot really make it to the in-person delivery. However, I'm going to give you guys some stuff to follow. So basically, it's going to be about proving the doubling strategy. I'm going to do the fixed increment strategy today, the constant increment strategy today, about how to derive its running time. And then I'll assign some questions for you guys to actually derive the one for doubling strategy. I'll give you guys some hints towards the end. So for you to actually do. So this kind of mathematical derivation will be something I will expect you guys to do, some part. Okay, so please do the exercise. It's not going to be very heavy this week. And then so today the plan will be, I want to do 3 things. I want to start with doing that dynamic array with the constant increments exercise about deriving its running time. I'll do it from the beginning until the end together with you. I'll do some recap as well. First thing. Second thing, I just want to, before we end the review lecture on the asymptotic analysis, I want to mention just some mathematical properties for big O, right? It's, again, it's maybe something you already learned from 2101, but it's really important to brush up so we can use those facts maybe later when we talk about other algorithms. That's number 2. Number 3, I'm going to start with a new lecture. It's something called self-balancing search tree or binary search tree, self-balancing. So today I wouldn't really get to the self-balancing part, but hopefully I can give you at least some basic definition about the tree height balance property. That's something we should really review or introduce to you if you haven't learned it before. And then I'll just hopefully show you a little bit the idea about rotation for the trees if we have time. If no, that's okay. We can definitely start from scratch for Monday. But for next Monday, so please make sure you bring a piece of paper with you. We're going to do lots of drawing about the tree rotation. In the lecture, we're going to learn about how to draw the tree rotation. It's going to be fun exercise for us on the paper. And in the tutorial, I'll try to design some programming exercise for you to think about how you might do tree rotation translated from paper into Eclipse. That'll be for not the coming Friday, but next Friday. You can look forward to it. Of course, I'll deliver that in person. I'll do some programming exercise together with you. Okay? It's going to be fun. All right, that's roughly the plan. Okay, we'll see how much we can get to. If I really cannot get to the tree rotation discussion today, don't worry, I'll do that Monday. Okay, it's going to be the agenda for next week. All right, so let's do a very quick recap from last time. So we're still kind of doing an asymptotic analysis. So we basically tried this alternative definition of the big O. So basically got definition number 1 with some diagram and also definition number 2. So this one here is pretty much standing alone. So it's really a good way to really review the logical operator you kind of learned from 1019 or 1090. So please make sure you at least understand how this one here can be understood. Especially the exercise I really want you guys to try. Of course, you can reach out to me if you got any trouble. Is to think about why we are using implication here as opposed to conjunction, right? So the hints I went over with you is to really look into the truth table for conjunction versus implication. Try to look at the different scenarios where these two logical operators will differ and see where you can interpret the reason why you should really use implication as opposed to conjunction. All right, that's my hints to you. Do try this exercise, okay? You don't want to really try it in the test, right? So that's something I want you to try. And this diagram here is very important. Of course, it doesn't really exhaustively list all the running time function, but these are the common ones, right? So we got constant, logarithmic, n log n squared, n cubed, and also exponential, right? That's really the brute force way of doing things, which can work, but very inefficient, especially for large size data towards infinity. It's simply not feasible when you get to exponential, right? So that's something we'll see also later in the course for different algorithms. All right, so we talk about 2 very useful little formula. So especially when you want to somehow observe the pattern for your algorithm involving a loop. So whenever you want to really analyze the running time for the loop, you want to see what's the lower bound and upper bound of the loop counter. So in that way, you can actually see how many iterations you're going to have. So we got closed interval between A and B, right, inclusive. And we talk about that's the little formula you should know. All right. And we talk about arithmetic sequence sum, right? So if you actually got some common difference between every term in the sequence there, and we'll see that actually in the fixed increment, or constant increment strategy for dynamic array, we'll see exactly this kind of sequence. We're going to see once more, right? So that's something I want you guys to also get familiar, right? There'll be one formula. In order for you to solve the tutorial exercise for this week, which is about doubling strategy, you will need some formula for geometrical sequence. That's something I will also derive together with you just in class today, so you get prepared for the tutorial exercise, right? I'll get there a little bit later. All right, so the formula here, the way I remember it, is the first term in the sequence plus the last term in the sequence, and then you want to know how many turns I have in total, and then multiply divided by 2. That's the formula. Okay? And we did this exercise here. So given some algorithm or just some code, you want to derive the asymptotic upper bound. So the interesting bit about this exercise here is you can see we got double nested loop, right? And the first loop counter I start with 0. However, the second one here starts with I itself. So the two loop counters somehow work together rather than being incremented independently. So that's why you got to be extra cautious. Of course, if I only ask you about what's really asymptotic upper bound, that's the tightest. You might just say n squared. That's okay. However, when you really want to derive to see what the running time is, you ought to show the pattern of the loop counter. So that's why we kind of did this exercise over here, right? So that's really something you want to go over. So we actually got 2 dimensions. The first dimension is about the outer loop, I here, which will be from 0 all the way to n-1, right? So that's the first one. So that means we got 0 all the way to n-1. We got n rows to consider. For every iteration where I is certain value, right, we're going to run the inner loop right here. So the inner loop here, we got j. So j here doesn't necessarily start with 0 all the time. It starts with the current value of I. So that's why in the first row, where I is equal to 0, we got 0, 1, 2, etc. In the second row, where I is equal to 1, j will be starting from 1, 2, 3, etc. Right? And the important thing is, since we are trying to observe about the patterns for these 2 variables, so that means for every combination of I and j, for example, let's say 0, 0, 0, 1, and also 0, 2, all the way to 0, n-1. Every combination there corresponds to a single execution of line number 5. And we know that line number 5 here takes only constant amount of time, right? That one only involves array indexing and variable assignments. So now the question is, in order to figure out the running time for this for loop right here, we ought to know exactly how many times this line number 5 is going to be executed. To really figure that out, we need to find out how many combinations there are between I and j, right? So that's why we figure out n combinations, n-1 combinations, all the way to 1 combination, right? So once you add up all these numbers, which happen to be a nice arithmetic sequence, right? You can see from here to here is -1, common difference. n-1 to n-2 is actually -1, etc. Right? So we can apply the formula very nicely. And then, of course, eventually, once you get an answer, it should be also big of n squared. But here, what the value really is to show the derivation process, which in the test, or maybe in the exam, that's also something we would like to see. Or maybe I might ask you the process in a different way, right? Depends. But you ought to know the process here. All right, any questions? We're good? Okay, good. And then, after this, we actually... we talk about implementing stack and queue. Okay, let me just set the general context again. So I'm going to go over some code, and then we can nicely transition to today. So we're talking about we want to implement either the last in, first out stack or first in, first out queue, right? These 2 data structure we wouldn't review anymore. That's kind of basic ones from 2101. So there are 2 ways to really implement these 2 data structure. Either you can simply use a fixed size array, in which case, once you fix the size of the array, you cannot really expand it when the array gets full. In that case, let's say you keep pushing elements into the stack. As soon as, at this point, maybe you already reached the maximum. In that case, doing 1 extra push is going to trigger some precondition violation. In Java, precondition violation will be some exception, like a stack full exception. That one's pretty straightforward. So what we're building here is right here. We want to somehow have the kind of array that will be expanded dynamically, meaning that you ought to have some if condition in your code to say, if the current size of the stack already reaches the current maximum or current length of the array, you ought to somehow grow the size of the array. Not only to grow it, but also you want to copy over all the existing elements in the stack into the new array, and then do some reference reassignment. I'll review that part again, okay? But that's really the idea about dynamic array. So all the code is already on the slides. Please take a look, especially when you do the tutorial exercise for this week. You also want to dive a little bit deeper into how the doubling strategy can be implemented. It's actually implemented in a very similar way as the fixed constant, like a fixed increment. So we got either 2.1 constant increment. That's something we're going to finish discussing today. And then I'll give you a little bit of quick intro about doubling, just to show you very quickly the essence of the change we are adopting. And then your exercise for the tutorial this week, again, there'll be no in-person attendance this Friday. I will send you some material for study, okay? But I'll resume the in-person delivery next Friday, okay? So doubling, okay? And something I want to mention once more, I think I'll try to make this remark again after the derivation for the constant increment. When you actually compare these two strategies, eventually, once you have done all the derivation mathematically, you ought to somehow conclude like which one is going to be more efficient asymptotically. Okay, so one intuition you want to build into Y. The second one I can even tell you, 2.2 doubling is actually more efficient. It's simply because since you're doubling the size each time, it turns out when you actually got a very, very large number of pushes, let's say in that case, doubling strategy is going to make resizing less frequent compared with the fixed constant increment, right? So that's the insight. I kind of put it over here. And that's something you can also try to look into to see how that can be reflected in the actual derivation for the math. Okay, that's something I'll try to show to you maybe once the tutorial exercise is completed. All right, any question, just in general, about dynamic array? Okay, dynamic in the sense that you can modify the size of the array as whenever necessary. Another thing, you don't really resize the array for every single push. You only do that for certain push when the current push is already exceeding the maximum capacity for the array. Okay. All right, so let me, okay, let's go here. All right, so that's the increments method that we are trying to study last time. So let me start from here. Okay, so let's look at the code very quickly, and then I'll make some more annotation. So what we're doing here is, there's a word here I want to mention here. So it's called amortized analysis. I think the word, you might see that more often in accounting, right? Amortized simply means average. So what we are focusing here is not really the worst case running time for this particular case study. We want to see what's the average running time for the push, okay, right here. You can think about this, it's really like a calculating the average running time, which conceptually is really about the total running time. You can think about the total running time is about adding the running time for individual pushes over some period, okay? The total running time, and then divided by the number of operations. Remember, last time I kind of asked you guys to kind of consider we got n pushes in general, right? So let's say we somehow add up the running time for individual n pushes. We got some number. Whatever that number is, divided that by n. So that will be the average running time. So over here, in our particular scenario, the number of operations could be, for example, n pushes for stack. If you want to do the similar analysis for queues, it will be the number of in queues operations. And then over here, the total running time. Let me also make some quick annotation. Okay, I'll put a star here. Okay, the total running time is going to be over a sequence of push operation, a sequence of. So we don't really just consider an individual sequence. Sorry, just not in an individual push operation, but over a sequence. Push operations. Okay, that's very important. Since we talk about average, right? So let's see this. If you look at the class here, so we got initial capacity of the array. So we first of all create this initial array. No resizing will be needed until we actually filled out the entire array, until we actually got the first I pushes, right? After the first I pushes, we're going to do some copying and then freed up some space right here with C. The C is a constant we set. C can be any constant, right? So we got C here, and then we got the current capacity, and we got the array, right? So that's something we set last time. And you can also plug in some number, right, for the actual program, okay? So now I want you to look at this push right here. This one here, okay? I want to distinguish between average running time versus worst case running time. So these two things are different, okay? I want it to be clear. Let's say back in 2101, right? Let's say you're only doing something like a 2101. If I consider this particular method here, and then we said you should really look at, of course, not best case, right? Best case you should never look at. Best case might just be constant, right? Which is very inaccurate. What is the worst case running time? Just this one here, just by looking at the code. Number one, you're going to tell me what is the worst case running time. Number two, where does that most expensive operation come from, or block of code come from? That's very important. Okay, I'll start with you first. Tell me the worst case running time first.
Is it N?
Okay, is N which part?
The copying.
The copying of the array. Yeah, exactly. Okay, I think your fellow student answered exactly right. Okay, I'm gonna write it down. It's going to be big O of N. You can think about the N here is really about the number of elements in a full array. Because if the current array is actually full, in that case, we have already reached the maximum capacity. So you can think about the capacity here is the N. Okay, the input size. And then you can see inside the loop, here, we're actually going to do variable assignment corresponding to starting from 0 all the way to capacity minus 1. So that's exactly capacity, right? So that's big O of N. Okay? So the worst case tells you that whenever you want to do resizing, that particular push that triggers the resizing is going to be the worst case. Okay? I'm going to write it down. Okay, I'll write it down here. At runtime, the worst case running time of a dynamic array running time of the push operation, let's say, occurs when that particular push, when that push operation triggers the resizing. And we know that the resizing is actually going to copy over all the existing contents into the new, bigger array. Need to copy the existing contents to the new, bigger array. So we talk about worst case running time. However, what we want to do is we don't really want to just consider worst case, because in this case, we don't really, worst case only talk about only certain push operation, which does not happen that often, okay? So if you think about it, like in this. So let's say if the initial size of the dynamic array is only 5, let's say. So when we get push, 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 and push. So let's say assume the capacity, initial capacity. The initial capacity is simply 5. So out of the first 5 pushes, right? You can think about this one here is going to be big O of n, right? Because that one is going to involve actually, creating that, new array, okay? Oh, to be more precise, actually, beg your pardon, it was not exactly right. Because if you look at the condition there, we only do the resizing when the size is exactly equal to capacity. So it's the next push. Okay, I apologize. That's not exactly right. So the push. You can see that over here, this will be big O of n because the size is exactly equal to 5 right here. Okay. However, on the other hand, what about all the other pushes right here? What's the running time? Let's go back to the code, right? So if you go back to the code, this condition is not satisfied. So we haven't really got the array to be completely full just yet. In that case, all we got to do is just right here. Just increment the counter and then do the assignment just to do the push. So this part here is big O of 1. So this will be the running time when resizing is not needed. Okay. So these are big O of 1, big O of 1, big O of 1, big O of 1, and big O of 1. This is the worst case. However, if you think about, I got 1, 2, 3, 4, 5, and 6 pushes. If I somehow add up their running time altogether, divided by the number of operations, which is roughly about n, I'm going to get just constant. Okay, something like that. I'm just kind of give you the intuition. The actual math is going to be more complicated, right? So my point is, in this case, it doesn't really make sense to only look at one particular push in isolation. That's the worst case. You can also answer that. But I'm saying it makes to be more fair to evaluate the resizing strategy. You want to look at a series or sequence of pushes to see what's the average. That's something we're going to do mathematically to be more precise. Okay? So it will be a more accurate assessment of the strategy by considering average case. That's something we'll derive together, right? I'm just trying to give you some intuition first. Okay. Right here. Good. Okay, so let's see if there's anything else to say. Yeah, you can look at the code, please, and then make sure you kind of understand how things are going to work. So at this level, maybe I don't need to go over like a line by line with you. That's definitely something you can trace. Let's now move on to mathematical analysis, okay? And we are making some assumption, okay? And just in case you're wondering about what this really stands for. Okay. Without loss of generality, okay? So I'll put it, okay, make sure I got enough space, okay? Without the loss of generality, Generality. So we are only considering n consecutive pushes. But in reality, you might get some interleaving between push and pop. That's okay. But we only look at a slice of the sequence where we only got pushes. That's enough for the exercise. All right? So we talk about n pushes. And then we're assuming that the very last push is going to trigger another resizing routine. That's the ending point for our consideration. Right? You'll see once I visualize the stuff, right? But just remember, we got some assumption here. Otherwise, it would be very complicated to consider interleaving with the pop as well. We don't need to. So just to get an idea, we just consider consecutive pushes. Go consecutive Okay, let's start from scratch right here. All right, we're going to observe the pattern. We have that initial array, which is completely free. So green means we got everything available, every slot available for us to store things. Okay. And then let's say after certain pushes, right? Maybe after I pushes, you can think about from here to here. After I pushes, that means we got this part of the array completely full. So we reach the maximum capacity. So now what we should do is we should really do some resizing, right? In the next push. So this is going to trigger that we're going to expand the array to be I plus C and then copy everything over into here, right? That's what we should do. Okay. All right, right here. So now for the very first resizing, exactly how much work should we do, right? It will be just about I, the running time. I would just correspond to copying all the I elements into the first I slots in the new array, right? That's really the loop that we're talking about, right? That's just I, okay? That's something we kind of did in the very end on Monday, but I was kind of in a rush, so that's why I'm doing that again. Okay, that's first resizing. And then what about the second resizing? So for the second resizing, it's after another how many pushes? Is it I or I plus C? Not exactly I plus. Okay, you're getting there. Think about this one here. That one was already full, right? So we don't really push to there anymore. So it's really like another C, right? Another C pushes, right? Okay, but you're on the right track. Thank you for trying. Okay. So this one will be actually after another C pushes. Every time onwards, it's going to be after another C pushes, another C pushes. After every C pushes, you're going to resize, basically. All right? And to really go from here to here for the resizing, how much work is needed? Would you agree? It should be I plus C, right? Because after the resizing, we are going to get this part over here. This part here should be completely occupied, right? We're going to copy that into the new array, basically, right? And then I plus C. That's correct. Okay? I plus C. Okay? I plus C. Okay? And then let's just do one more. And let's say we do another C pushes. So after another C pushes. So that means we got right now here. Right? So what we want to do is we want to somehow copy all these things over into the new array. And then with this additional space. Right? So that'll be I plus 2C. Agree? Okay. That's enough for us to somehow generalize the pattern, but I'll do that in just one moment. I plus 2 times C. Okay, I'm just helping you to really identify the pattern. You will do something very similar when you do doubling. Okay? So let me rewrite the very first one slightly, and you can see the pattern even better. Think about this one here is I plus 0 times C. And this one here is really I plus 1 times. Right? So you can see right here, 0, 1, and 2. Okay? Right? And these kind of multiplicative constant for that constant there correspond to something. You can see in the very first resizing, it's 0. Second resizing is 1. Third resizing, it is 2. So if we say we actually got different resizing steps. So let's say we got something called K. And K is the resizing step. So this is step number 1. This is step number 2. And this is step number 3. And all the way to the very last one, right? You can see that when k here is equal to 1, this constant here should be k minus 1, 1 minus 1. When k is equal to 2, this one here is 2 minus 1. And when k is equal to 3, k minus 1, right? So that's a pattern I'm observing. So far so good? Okay. And of course, you cannot really just move on like that because we are doing some general analysis. You gotta somehow stop at the first few, and then you should really go on, say dot, 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 and go to the very last resizing and try to see how you can figure out the pattern for the very last one. And then we will be ready to add up everything together. Okay, let's look at the last one. Okay. If you look at the last one here, I said n pushes. N pushes simply means we should have got n elements already occupied in the array, right? Let's take that insight. Right? This is very important. I want to go a little bit more slowly here. So after n pushes, that means the first n elements store in the array. After the very final step right here of resizing, which part should be free space? Like a green. C? From the left or from the right? From the right, right? Right here, right? Good, okay. That's obvious, but I want to double check, right? So here, think about this is really the part after the resizing, right? So this will be free. Other than that, this part over here should be completely occupied. So I plus a bunch of C's. That one there should be exactly equal to n. That's very important. What does that mean? Let me just try to help you interpret, because now we got so many variables, right? You don't want to get lost. This will be the result after the very last resizing. And we know that the very last resizing is somehow triggered by after n pushes, which we assume. After n pushes, we know that there should be exactly n elements in the very first n slot in the array. So that should be exactly right here. And then this C here is, like before, is exactly the additional fixed constant space we have created after the very last resizing. Okay? However, this one here, we ought to know what it is. Right? That's something we'll try to see. And one question for you. Which step is this? We got 1, 2, 3, all the way to something. But what's this number here? K is good. Yeah, but what's K? I like K. Actually, it's good. You know, in some way we should put K here. I agree. Nothing wrong with that. Guys, this is tricky. So if you don't really follow exactly, that's okay. That's why, I want to review this. Okay, one moment. Okay, I'll write down K. But the thing is, what is K? Go ahead. Yeah, go ahead, please.
N minus 1.
You're getting somewhere, so it will be n minus 1 somehow, but not exactly n minus 1. You're thinking on somehow on a similar track, right? N minus 1? Somehow, yeah, it's good. Yeah, similar. Okay, it's okay, don't worry. Yeah, most likely this is your first time encountering this. This is tricky, so I think it's good enough, right? So thinking this way. If this is K, so we got 1, 2, 3, all the way to K, right? We said earlier, the amount of work that we have over here should be exactly the step number minus 1 here. Agree? So now, accordingly, if you think about right here, what would be the amount of work? It would be I plus what times C? K minus 1, all right? Because K here is a step number, right? Remember 0, 1, 2 correspond to exactly a step number minus 1, right? That's a pattern we observe, okay? So let me put it down, okay? So that would be exactly K minus 1 times C. And then we know that this here is exactly equal to that, equating these two together, we will be able to solve k. And the k here is important because k here tells us how many turns there are in this particular resizing. We want to add up the running time for every individual resizing step. All right? So let me say it one more time. We first of all know that this part here should be n because after n pushes. At the same time, we know that this portion here should be exactly equal to this equation here because we observe the way every resizing is going to work is going to be I plus the resizing step number minus 1 times C. That's also the pattern we observe, right? Let me write down this equation, okay? So this one here and also this one here, right? So we say the following. So we say n is exactly equal to I plus k minus 1 times C. And once we have got this one here, we can rewrite it, right? The k will be exactly equal to, okay, I'm going to rely on you to really double check, right? I can tell you what it is. It is exactly like this. N minus I divided by C plus 1. So when you guys say like an n minus 1, I'm kind of getting there, but not exactly, right? But we want something precise. Okay, that's k. And the k here is so important because the k here tells us about how many resizing steps in total are really needed. In order for us to really calculate the summation of the arithmetic sequence, we also need to know how many turns there are, right? So also good? Okay. So now let's write out the whole thing, okay? So the whole running time is going to be the first resizing plus the second resizing all the way to the very last resizing, which we know is n. How many resizing do we have exactly? It's going to be k, which is this number here. Okay, let's now write it down. Okay, so the total running time will be the summation. This one is a little bit informal, just a sigma, right? The summation of all the resizing steps. Which will be equal to, let's write out the sequence over here. So the first one will be I plus just I. Okay, I'm going to just put I back. I plus, and then the second one, I plus C. Plus I plus 2C. Plus all the way to, now the very last one. We know the very last one is simply about n pushes. So we got exactly n element to copy over to the new expanded array, plus n. All right? And apparently it's an arithmetic sequence with, what's the common difference? C, right? Plus C, plus 2C, right? That's exactly common difference, right? So what we should do is beginning plus the end, multiplied by number of turns divided by 2. Okay? So what we do is this, which will be equal to beginning plus the end multiplied by the number of turns, which is the k. I'll try to write it a little bit better. Okay, so this part over here, sorry. So this part over here, okay, already here, multiplied by, it will be n minus I divided by C plus 1, okay? And then the whole thing divided by 2. Okay, let me just help you understand again. So beginning right here, the end right here, the number of turns, which is the k we derived, and then divided by 2, okay? What is that? Well, of course you can calculate, right? So let me say this, okay? There's something I want you to double check for me, okay? I'll write down something here. Star, okay? Double star. I'll put some number here. The double star, right here. So it's actually n squared plus c times n plus c times I minus I squared divided by 2c. That's the precise. And now, what's the asymptotic upper bound for that? N squared, right? Of course, that's the answer. But to really show the work, you got to go for that detail, right? Because that's the highest power. So this is the highest power. Okay, big O of N squared. Okay, so this one here is big O of N squared. However, big O of N squared is not the final answer because this is the total running time over N pushes. If we want to calculate average, divide that by N. So the amortized or average running time that we're going to get right here, I'm going to put that into this box over here, is going to be the big O of N squared, which is total running time, divided by the number of pushes that we assume, which is N. That one is going to be big O of N. So that's the final answer. Don't lose the big picture. What we show is as follows. If you only consider the worst case running time for the push, it's actually big O of N. And sometimes you got to be big O of 1. However, if you try to calculate amortized average, it turns out also big O of N. But when you actually get to maybe the doubling strategy, you will see something that the average running time is going to be much less. That's something you will actually try to do in a tutorial exercise. Okay? So here it just turns out average and worst case are the same. But they may not be the same, depending on the strategy we are choosing. Okay? So what are you supposed to know from this derivation here? Number one, about the difference between dynamic array versus non-dynamic array. Number two, how the constant increment strategy will actually work in terms of the Java code, right? Like an algorithm, the implementation. Number three, about the difference between the worst case running time versus the average case running time. Number four, you also ought to know how to derive the whole thing. Okay, that's something we already went through one of them. The other one for you to do is for the doubling. And doubling, I just want to mention something very quickly. Do I have the code right here? I don't, but for the doubling there, I'll show you the slides very quickly. Okay, for the doubling, that's what you will see. The only difference is you can see now when the capacity is reached to be the maximum, what we do is we create an array of double the size. Implementation-wise, it's not much different. You can change about a new size. But when you derive the running time here, you have to be careful about how to figure out the number of turns for the resizing. It turns out the number of resizing is going to be much less than the fixed increments. And the average running time accordingly will be much less. I can even tell you, if you actually get an average case running time to be constant, big O of 1, that you're on the right track. Okay. All right, guys, any question about dynamic array? So I think that this will be a very nice first addition to what you learned in 2101. We're definitely doing something more sophisticated, right, in terms of math. Not even about unfolding like a recursion. We're just doing some summation here. But you can really do many things for the algorithm. All right, any question before I move on? We're good? Awesome. Okay. Why don't we take a short break right now by taking attendance, and then after break, I'll talk about some properties of big O very quickly, and then we'll talk about self-balancing binary search tree. Okay. All right. Since we only got 30 minutes left, I'll rather do the following. Okay. For the big O property, we can do that later because that one's really simple, more like a review stuff. I'd rather we do something a little bit more like a newer to you. So I'm gonna just do quick, just about deriving the geometric sequence sum together with you, because for you to really come up with the running time for doubling strategy, you will need this formula. So let's derive that together very quickly. And then after that, I will get to a new lecture just about self-balancing search tree. Let's talk about the introductory part, just review quickly about the high balance property. And also I want to show you a little bit about rotation for the tree. That's going to be interesting, before next Monday. Okay, let's do this sequence. And for the big O, we can revisit that maybe a little bit later. That should be good. Okay. Right, so this is the second formula, third formula. We learned about interval size and also arithmetic sequence sum. This will be the third one, geometric sequence sum. So one example could be, for example, let's say you may have, let's say we got 3 here. And, okay, so let's say if we got 3 plus maybe 6 plus 12 plus 24, etc., right? So there is an initial term, there's a common factor, there's a number of terms, etc., right? So you can think about this is like an initial term. Okay? And then when you go from here to here, there is some common factor. From 3 to 6, you actually got 2. From 6 to 12, I'll multiply by 2, of course. This will be multiplied by 2. And this one here will be multiplied by 2, right? It's rather than common difference, it's more like a common factor, okay? And you can also think about this one here, of course, it's more like, okay, I'll use a different color. So this one here is like a 3 times 2 to the power of 1, okay? This one here is like a 3 times 2 to the power of 2, right? And this one here is like a 3 times 2 to the power of 3. But of course, if you like, you can also think about this is 3 times 2 to the power of 0. The number of terms in this case would be 1, 2, 3, 4, 4. However, 4 here nicely correspond to the exponents that we have. You can see we got 0 here, we got 1 here, we got 2 here, we got 3 here. So what's the interval size from 0 to 3? 4, right? So one very important insight for you to figure out exactly the size of a geometrical sequence is to look at the exponents when you kind of rewrite each element like that, right? Just remember that insight, right? So that's just one example, just to make it very concrete for you. But let's now write out a general formula, okay? So what we have is, let's say we have some sequence with k terms. That means ultimately the exponent there should be k minus 1. Right? Go from 0 to k minus 1 for the exponents. So what we have is the initial term plus I times r plus I times r squared. Right? You can see the exponent just keep increasing. Let me just get one more. Plus I times r3. Plus all the way to I times r. What should be the last one? If we got k terms. K minus 1, right? Good, thank you. Yeah, exactly. Okay. Yeah, just watch out the precision. Good. Quick annotation for you. So this one here is the first term. And this one here is the second term. And this one here is the third term. And this one here is the fourth term. And this one, last one here is the kth term. Right? Since we got k right here. Right? And then, if you like, you can also rewrite this one here to be I times r to the power of 0. Because r to the power of 0 is simply just 1. Right? Now, how do we derive the sum? Right? You basically do a little bit trick here. You kind of multiply this sequence here by the common factor r. All right, so let's see how that's going to look like. So we'll simply do r, the common factor, multiplied by sk. So think about what's going to happen here. So for this one here, if you say I multiplied by r, it's going to be I times r, right? So I'm going to put in this way, just easier for you to see. So I here, once you multiply by r, is going to be I times r. I times r. And then for this one here, I times r here, if I times r, again, right, every term. So you can think about this term times r becomes this. This term times r is going to become this, right? So this one will be I times r squared. And this one here, multiplied by r, is going to give you I times r cubed. And this one here is also going to give you, this one here is going to give to you I times r times 4, right? Okay. So you can think about there is what's the term before this? Is I times r to the k minus 2, right? If that one times r is going to be exactly this term here, right? So you can think about this term here. If you try to multiply by r, it's going to be I times r to the k minus 1. And finally, if this one times r, it's going to give you I times r to the power of k. So think about here, we got exactly, So here we got exactly k terms. Here we also got exactly k terms. But because of the multiply by r, you can think about it's almost this sequence, almost, except this one is gone. And this whole thing is right here. And we got some extra term. Right? So you can try to convince yourself. Yeah. I wish I could outline a little bit better, but you can do better when you try to practice this yourself, right? And then we're just going to identify the common, identify some block here. Let's say right here. This part over here is exactly the same, right? So the only difference is we got I here from the original sequence. We got I times r to the k from this new one here. Okay? So what we do is we're going to kind of subtract them from each other. Okay? So what we do is we're going to say we're going to have s r times sk minus sk. We're going to subtract this one here from this. That one there, if you factor out sk, you actually got r minus 1 times sk. Right? And what is that one? So that means this part here is completely canceled out. So we got this one here minus this one, which would be I times r to the k minus I. And factor out. Factor out I here, which will be I times r to the k minus 1. Okay? So what we got is this. We say that this one here, let me use a different color. We say that this one here is this one here. And then equal to, so that would mean sk will be exactly equal to this one here divided by this multiplicative constant, right? I times r to the k minus 1 divided by r minus 1. And little exercise for you, okay? Apply this formula here to this sequence over here to see if the sum will actually match for the formula. I'll let you try. It should match. All right? That's the formula. Okay? So the formula was kind of applied in our 2101 earlier just for binary tree, right? Especially when we want to calculate about the number of nodes in each level. That's what we needed. But I think that this formula will also be handy, especially when you calculate the running times for resizing in the case of doubling. That's something you will see. It's going to be very useful. Okay, I'll give you the hints right here. This will be useful for the average running time of doubling strategy. All right. Any questions about this? We're good? All right, let's now start a new lecture. As I said, the big O properties, I'll do that maybe maybe a little bit later. We'll find some spare time, sometimes in the lecture, to cover those properties. They're pretty straightforward. But I just want to talk about, in about 20 minutes, I can talk about some high balance property and also do some tree rotation. Okay, that will be more interesting use of the time for today. All right, so this one's done, but I'm going to give you the tutorial exercise related to the doubling. Okay, I'll make sure I release it before the tutorial time on Thursday. All right, self-balancing binary search tree. You can already see the slides on the lecture side. However, don't really try to print it out just yet if that's your intention, because it's still incomplete. I'm going to add a little bit more slides before Monday. So in order for us to really see this one here, we need to understand two things, which I also need to review. I'll do one of them today. The thing we're going to review today is about high balance property. What does it really mean for a tree to be high balanced? Okay, that's something we're going to do today. Number two, we ought to review about how to do insertion and deletion on a binary search tree. Especially for deletion, there are several cases that we have to handle, right? So that's something we also got to review. Once we review these two things about the binary search tree, we can then talk about when you try to do insertion or deletion, that might cause the tree to be unbalanced, which is going to cause eventually maybe linear time for the insertion or deletion. In that case, how should we somehow fix the balance right away after that insertion or deletion? Right? That's something in tree rotation we got to do. Right? So that's something we'll gradually talk about. It's going to be a whole series. Okay. Let's now go over some slides, and then we'll actually do some exercise on the insertion deletion, just some basic one, just to see the idea. We're going to talk about worst case running time. We're going to see right away to see a binary search, high balance property, and then to review about insertion deletion, we'll do that on Monday. Okay, we can do that very well, not quickly, but I gotta just do that properly. Just make sure you understand. And also rotations. That is simply is definitely something new for us to learn. Okay, so motivation really is whenever you want to do insertion or deletion, anything that has to involve something about binary search. Because as part of the routine for insertion or deletion on a binary search tree, you have to first of all do a binary search. And the binary search itself might be linear if the heights of the tree happen to be linear. If the height of the tree is not log n, then you're going to have some very costly insertion, deletion, and search, right? So that's really something we kind of learned from the previous course, but we'll review. So this slide here just kind of show you some examples about how you can result in some tree that's ill-balanced with linear heights, right? Let's just see that quickly, okay? Let's just go over some simple example there, but when we try to do tree rotation later, we'll see more examples, okay? Oh, so this one we'll do later, okay? Just right here, okay? Right here. I'll do just one example here. So let's say we want to somehow construct a binary search tree by inserting the key values in this order. So think about, let's say this one here is the key, a key value. Okay. How do we insert that? So we start with 100. So we start with an empty tree. And then we insert 100 first. And then we want to insert 75. Now, 75, should it go to the left or the right? The left, right? Because the search property, right? So that one should really go to the left, 75, right? So far, this is a binary search tree. Because when you do an in-order traversal, you're going to get 75 followed by 100. It's a sorted sequence, right? That's how you check to see the search property actually is there. And then insert 68. It will end up being right here, 68. So you can see 100, go to the left, 75, go to the left, you got 68. Again, you get in order traversal 68, 75, 100, okay? And then similarly, 60. And then 50. Oh, okay. And then just 1. So now we got all the elements. So in this case, the number of element is 1, 2, 3, 4, 5, 6. Okay? What about the heights of the tree? The height of the tree is about the number of edges from the bottom leaf to all the way to the root. So we got 1, 2, 3, 4, 5. So the height is equal to 5, which is about n minus 1. So it's a big O of n. So this is just one simple example to show to you it is possible, if you're not careful, to really have certain insertion and then you have a certain sequence of insertion without any adjustment in between. You just got some tree of linear heights. And for this one here, linear heights results in big O of n, search, insertion, and deletion. That's why you got to be very careful. So whenever you say you want to do binary search, all good. I got to make sure if you're implementing binary search on if you're implementing binary search on a binary search tree, you got to make sure the height itself is log n as opposed to linear. And you can try these two exercises, just to see, right? So it just gives you different flavors about how the tree can be created as not balancing. Okay, so these two will be exercises for you. Okay, give it a try. Okay, right here. And let's now take a look at the next one, which is about high balance property. So this one here as a formula, just to remind you about what does it really mean for the heights of a particular node or a subtree. We're going to just use the example, but you can review the definition. Okay? So here is a high balance property. Let's go over that and I'll show you visually how you can do the exercise. Okay? So a binary search tree will be called a balanced. Okay, let me just write it down here. So when you say a binary search tree, and then plus the high balance property, that one there is going to give you a balanced binary search tree. And this one here, let's just take a look and we take some notes together. That one tells us every internal node, we only consider internal node, we don't consider external node. Okay? Every internal node, the heights of their children should be differ no more than 1. Okay? I'll write it down first and then we'll see how to see that visually. Okay? The difference for every internal node, for every n, okay, n is internal because he has at least one child, right? The difference of heights of n's children should be less than or equal to 1. Okay, there are two parts. Number one, we only consider internal. And then number two, we want to make sure the heights of their children should be different no more than 1. If there's more than 1, like a 2 or 3 or 4, we got to watch out. Okay. So the idea would be as soon as the high balance property is violated, we should do something, which is called rotation. That's something we'll definitely cover next week about how you can do rotation. Okay. Okay, given this, let's do some quick annotation, just about exercise. We'll see. Okay, I'll just put this one. No. Okay, so let's start with balancing. Okay, let's take a look at this. We'll look at actually 3 examples. I'll go over each one of them with you. Okay. So let's say this. The way to really annotate is this. So there's some conversion we're going to follow for the binary search tree. So we got internal nodes, which stores the key value. Okay, internal nodes, right, over here. And then you also see that internal node also got some external nodes. External node will simply use a circle to really express. Okay? External node usually does not store any value just yet for the key. So this will be actually very useful. I'm going to review that part on Monday. So this kind of implementation will allow us to store things in here as a new key. Okay? That's something I'll review on Monday. But for now, let's just take it for granted. Okay? So the way to really check to see whether the tree at the moment is actually balanced. Oh, before that, is it a search tree? 5, if you do in order traversal. 5, 17, 32, 44, 48, 51, 56, 77. It's an in order traversal. It's a sorted sequence. So it's really a search tree. But is it high balanced? Let's see. The way to do it is you're going to somehow go bottom up. Okay? To start with, annotate the heights for each external node to be 0. So I'm going to say 0 here, 0 here, 0 here, 0 here, and also 0 here, 0 here, 0 here, 0 here, and 0 here. Okay, and for children at the same level, we can immediately consider what's their height difference. Okay, for example, you can see for these two siblings right here, what is the difference of their heights? 0, right? 0 versus 0. And also for these two, the difference is also 0. Okay? And for these two, the difference is also 0. And for these two, the difference is also 0. We cannot go any further just yet because we haven't computed the heights for other nodes in the tree, but we'll continue. Okay? But at least as far as those pairs of the external nodes are concerned, their parent node, which is internal, is actually okay because the high balance is not violated just yet. How do we actually annotate the rest of the node? According to definition, the height of a particular node, if that's internal, is going to be 1 plus the maximum heights of its children. Okay? What will be the heights for this one here? The height of its children is 0 and 0. What's the maximum? 0. And then plus 1. So its height will be just 1. All right, let's try this one here. What's the height of these internal nodes? Maximum heights of its children, 0 and 0. Maximum 0 plus 1 will be 1. Okay, and then this one here, 0, 0, maximum 0 plus 1, we get 1. What about the height for this one here? 2, because here the children, 0 and 1, the maximum is 1, and then plus 1, you get 2. Okay, hopefully you get the idea. And 0, 0, maximum 0, and we get 1. And then 1, 1, maximum 1, plus 1, 2. And then 2, 1, maximum 2, plus 1, you get 3. Okay, 2, 3, maximum 3, and then plus 1, you get 4. All right, that's about calculating the height. I would say you don't necessarily have to consider the height difference just yet, maybe until you actually figure out the heights for all the nodes first. Okay, maybe figure out the nodes heights first before you actually talk about difference. Okay, and then let's now talk about the difference, right? For example, you can see over here between these two siblings, the difference is just 1, which is okay, less than or equal to 1. And then the difference right here is actually 0. Right? You got 1 versus 1. And the height difference over here, 2 versus 1. So the difference is 1. Also fine. And then you got the final level here. These two sibling nodes, the difference is 1. Right? So we also fine. And this one here, just itself, so we don't need to consider. So far you can see for every internal nodes, their child nodes have the height that's with height no more than 1. So the high balance property is nicely satisfied by this first tree. Okay? It is balanced. So what we'll do now is we're going to insert one node. And this insertion here, let's see if the insertion itself is going to make a tree that used to be balanced, not balanced anymore. All right? So we basically start with the same tree. All right? And then I'm going to show you explicitly, right? So with this tree here, the heights that we calculated, I'm just going to put it here, right? That's the height we just calculated. And we're going to see how the height is going to be changed along the way. Okay? So this one here, just let me annotate as well. So that's also 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, like that. Let's start with this. And then we want to insert 55. Oh, actually, insert 55. Where should 55 go? This will be some insertion routine I'm going to also review very quickly on Monday. Okay? So basically, you want to think about where should 55 go. 55, you do a binary search. 55 should go to the right, right? Compare with 56, you should go to its left, 55, right? And compare with the 48, 55 is larger, so it should go to its right. And for 51 compare with 55, 55 is larger, so we should go to the right. So this is the external node that we retrieved. So that means 55 should be stored in this particular external node that's returned. Right? It's a very quick summary, but I'll add more slides to really show you the review. Right? That's something you can also take a look. So what's going to happen is we're going to actually create the 55 right here. Okay? So this is going to be the inserted 55. That one's going to be internal. Accordingly, we should also get two external nodes right here. Circle here, and also circle over here. And we got 0 and 0. What we should do now is very critical, right? Since we have inserted one node into the tree, we need to update the heights along its ancestor path. We need to update the heights of the nodes along the inserted node's ancestor path. And we know the ancestor path is actually along this way, right? Along here. Let's update the heights. Okay? Let's start with this. Okay? So let's see this. Let me use maybe purple. Okay? 0, 0. So this means this should be 1. Right? And then we got 0, 1. This should be 2. And then 0, 2. Maximum is 2. So this one should be 3. And then 3 and 1, maximum is 3 plus 1, so this should be updated to 4. 2 and 4, maximum is 4 plus 1, we got 5. Guys, follow so far? Right? So we inserted one node to the bottom of the tree because the key doesn't really exist, and then we try to update the heights along the ancestor path. And now we need to identify if the tree is actually still balanced. And whenever you identify the tree being unbalanced, maybe it resulted from some insertion or deletion, you ought to find the lowest point when the tree becomes unbalanced. Let's see. Okay? So let's go this way. So this will be also part of the procedure, how you're going to do rotation when I'm going to cover on Monday. Okay? Let's say this. So 0, 0 here, I think the difference is fine. The difference over here is simply 0, so we're okay. And now here, you got these two siblings here. You got 0 versus 1. So difference is 1. We are also fine. right? However, if you look at these two, we actually got 0 versus 2. So the difference over here is 2. So this is definitely the earliest point where we see that there's a violation of the high balance property. Give me 1 minute, I'll finish that. We'll do the rotation next time, okay? And then you can keep going if you want to. You can definitely see that here we got 3 and 1, right? If you look at these two over here, the difference is actually 2, which is also violating the high balance property. And finally, if you look at 2 and 4 right here, the difference is actually 2. So that tells you there's also another violation. So we got 3 occurrences of the violation. So this node here has the heights of its 2 children larger than 1. And also this internal node over here has its 2 children, the heights difference more than 1. And also for this node as well, because the children height also differs more than 1. All right? So that's really something we want to fix. So immediately after this insertion here, we want to make sure the balance of the tree is restored right away before we take on any further insertion or deletion. That's something we're going to focus on possibly for both next Monday and Wednesday. All right? So little exercise for you. I know I'm running over time, so please bear with me. Okay? I'm going to finish it right away. So this one here will be some exercise for you. So try to do the insertion for 63 and decide whether you're going to get the tree out of balance. Okay? Exercise. All right, thank you so much. For Friday, I'm going to send you the exercise to try, okay, about proving the doubling strategy. Thank you. See you next week.